If we're asked to find an equation that satisfies this graph, then we use all the information that we have, and we start with our intercepts, which give us our zeros, which give us our factors. So our x-intercept on this side is -2, and then we have 1, and then we have 2. So it is -2, 0, it is 1, 0, and it is 2, 0. These are our x-intercepts. That means our zeros must have been x is equal to -2, 1, and 2. Okay? My factors then come from my zeros, so it is x plus 2. That's the first one. X minus 1, that's the second one, and x minus 2, which is the third one. We have to determine the multiplicity on these, and the way that we determine the multiplicity is how they behave at the intercepts. Because they're not bouncing, all their multiplicities must be odd. And if we're looking for the least degreed polynomial, then all of those have a degree of 1. Then we have to take into consideration is we don't know what the leading coefficient is, so I just put it as a. So what I have right now is I have my function is equal to a, x plus 2, and I can raise it to the 1 power. I can just put x plus 2, x minus 1, and x minus 2. So now I use some other point on the graph. I could use this point right here. That's an okay point to use. But I'm going to use that point because it's less work, because one of the two is 0. In particular, this is a point 0, 2. So I know that when I go to this, I can replace all of these. I'll do it this way. I can replace all of these x's with 0. So I'm going to use the ordered pair 0, 2. And I replace f of x with 2. That's my output. So what I have is 2 is equal to a, 0 plus 2, 0 minus 1, and 0 minus 2. So I have 2 is equal to, well, I have 2 times -1, which is -2, multiplied by another -2, so I have 4a. Now I just solve for a. A is 1/2. So I go back up to here. Let me get rid of some of this other stuff. So I go back up to this part, and I just replace out that a, because I found out what a was. I can't assume that a is 1. So I go back to this, and I just replace the a with what I found it to be, which is 1/2, and that's my final answer. Yeah, so I can use any ordered pair that I can easily see, like this ordered pair. I can use this ordered pair. I can use this ordered pair. I could use this ordered pair if it looks like it's probably on the graph. What you can't use is the intercepts, because you'll get 0 equals 0, which is a true statement, but it's not going to help you.
That's the step I forgot, was how to find the leading or the a. That's why I think it was.
Okay. What else?
Number 13.
Okay. Okay, so for this particular problem, what they're asking us to do is find all the zeros. So I make sure that my polynomial is in descending order, which it is. I start out with x to the 5th, and then from there I've got x to the 4th, and then x to the 3rd, so that's cool. I'm good with that. I have 3 terms, so I think it might act like a quadratic. It doesn't look like it right now, but it probably is. And the way I determine that is, can I factor out a greatest common factor? And the answer is yes. They all have an x cubed there. So I'm going to rewrite this as my function is f of x is equal to x to the 5th minus 4x to the 4th minus 56x cubed. I'm going to rewrite this as x cubed out, so I'm going to factor that out. When I remember when I'm factoring, what I'm doing is dividing out that value, my greatest common factor. So that means I'm actually subtracting exponents. So this is going to be x squared minus x minus 56. Once I do that, all I have to do then is factor the quadratic that's remaining. When I factor the quadratic that's remaining, as I'm looking for factors of 56 that have a difference of 1. So this is x and this is x. And I know it's going to be a difference because this is a minus. So I just need two numbers that multiply together that give me 56 that have a difference of 1. Well, what are the two numbers that multiply to give me 56 and a difference of 1? 7 and 8. So I have x minus 8 and x plus 7. And I know the minus has to belong to the 8 because my middle term is a negative. So if I were to add negative 7 and 8, I need to get negative 1x there. So then each one of these three factors, and I have three factors. I have this factor, I have this factor, and I have this factor. I have three factors there. So don't forget that my first one is x cubed is equal to 0, so x is equal to 0. My second one is x minus 8 is equal to 0, so x is equal to 8. And my third one is x is equal to negative, or x, I should do it like consistent, x plus 7 is equal to 0, so x is equal to negative 7. The multiplicity is the power on each one of those factors. So this has a multiplicity of 3. This has a 1 there, so this has a multiplicity of 1. And this has a 1 there, so that also has a multiplicity of 1. The biggest thing that I see when students don't get this right is they forget about this very first term, which is x cubed also has to be set equal to 0. You can't forget that one.
That's what I forgot.
And that's common. That's common when you're first learning these, and that's okay. As long as you fix that, you're good to go. If you make it the first couple of times, cool. Don't do it on the test. Yes?
3.2.
For this problem, what they're asking us to do is they're asking us to do synthetic division without being able to really put synthetic division in and of itself, right? We know that we have the coefficients in the first row. So all of these are the coefficients from here. And then they want us to compute p of negative 2. So what they're asking us to do then is they're asking us to do the synthetic division in which there's a negative 2 right there. So if I was doing the regular synthetic division, my first number I would drop down is 1. So that's what goes here in that A position. And then I would do 1 times 2, so this is going to be negative 2 times 1. So what's going to happen right there is that number is going to be negative 2. So that's negative 2. So that's what I'm going to put in the B. Then I'm going to add those two together and I get negative 5. That's what goes into the C. And then negative 5 times negative 2 is 10. That's what goes into the D. Negative 2 plus 10 is 8. That's what goes into E. Negative 2 times negative 2 times 8 gives me negative 16. That's what's going to go into F. And then negative 16 plus 1 is negative 15, and that's what goes into G. Okay? So when negative 2 is put in, your remainder is what?
15. Negative 2.
That is the value that comes out if you put negative 2 into the original function. So if you were asked to find p of negative 2, it is negative 2 to the third minus 3 times negative 2 squared minus 2 times negative 2 plus 1. This gives me negative 8, and then minus, I have 4 times 3, it's negative 12, and then this becomes plus 2 plus 1. Negative 8 minus 12 is negative 20. And then, let's went back. And so this should be here, that should be 4. So that should be 4. So negative 20 plus 5, well, what's negative 20 plus 5? It equals negative 15. So you can find the remainder by doing synthetic division. That's right here. Or you can put that number in, and that also is your remainder. So that second part is saying if you put in negative 2, the answer that comes out is negative 15, which is the remainder. If your remainder is 0, x plus 2 would have been a factor.
Where did you get negative 20 from?
So negative 20 comes from the fact that I have this is negative 3 times negative 3 times negative 3, which is negative 8. This is positive, yeah, positive 4 times negative 3 is a negative 12. It's that one. Negative 8 minus 12 more is negative 20, and then I have plus 5. So there are two ways that I can find the remainder. One is to plug that number in. The other one is to do synthetic division. So then, this is asking you for the quadratic that is the q. Well, what they're asking for is this part of the synthetic division. That would have been x squared minus 5x plus 8. That is your quotient. So x squared minus 5x plus 8 is the quotient. Your remainder is still negative 15. So it's leading you into synthetic division, making sure that you understand where all the numbers come from and what comes out. That's all it's asking you for number 1. If you were to take x plus 2 and you multiply it by that value that we did when we got synthetic, not the remainder part, but the value x 2 squared minus 5x plus 8. Now, if you were to multiply these two, then x times x is x cubed. X times negative 5 is negative 5x squared. X multiplied by 8 is going to be plus 8x. X multiplied by x squared is so plus 2x squared. X multiplied, or 2 multiplied by negative 5 is negative 10x. And then 2 times 8 is 16. Now, what I end up with is x cubed minus 3x squared minus x plus 16, right? My polynomial, however, is plus 1. So the way in which I get my polynomial that I start out with is I do need to add on my remainder. My remainder was 16 or 15. So my polynomial is x cubed minus 3x squared minus x plus 1. That's the polynomial that I actually started out with. And I can write it as this here. I can write my polynomial as x plus 2, x squared minus 5x plus 8 minus my remainder, or plus my remainder, which is a negative 15. This is my quotient. That's my q of x. That's the value I found when I did synthetic division. This is my divisor, d of x. We call that the divisor in class. And this is my remainder. So I can write my polynomial as this, but it's also equal to this. And the whole reason that we do this is it sets us up to be able to factor. Now, what we're going to be doing in class, so let's just use this example, is we have x cubed minus 3x squared minus 2x plus 1. So here's our function. Today what we're going to be doing in class is trying to figure out if I can find the zeros, right? The way I do that is I call this p, I call the coefficient q. So a sub n is equal to q, and p is equal to my constant. I list out all the factors of p. So the only way I can get to p is in plus and minus 1. I list out all the factors of my leading coefficient. The only way I can get there is plus and minus 1 because it's also 1. So my possible zeros are the combinations of P over Q. Well, that's just plus and minus 1 over plus and minus 1, so it's just plus and minus 1. These are our possible rational zeros. What I mean by that is we may have other zeros that are real numbers, they're just not nice numbers. I'm guaranteed to have one because it's a cube, but it may not be a nice number. So I'm going to put in, this is where I use my intermediate value theorem combined with my factor remainder theorem. I'm going to put negative 1 in there and see what happens. I put negative 1 in there, I get negative 1 cubed minus 3 multiplied by negative 1 squared minus 2 times negative 1 plus 1. Negative 1 minus 3 plus 2 plus 1. Does that equal 0? Well, this is negative 4 plus 3. This equals negative 1. Because that is not 0. This is not 0. That means x plus 1 is not a factor. If it was 0, then it would have been a factor. So now I'm going to try f of 1. So I put 1 in there. I get 1 cubed minus 3 times 1 squared minus 2 times 1 plus 1. So I end up with 1 minus 3 minus 2 plus 1, which is negative 4. Is that right? Negative 3. This is not 0, which means x minus 1 is not a factor. Because they're both negative numbers, the intermediate value theorem is indeterminate. My outputs, because that's what these are, this is an output, this is an output. Since they're both negative, my intermediate value theorem is indeterminate. I could have a 0 between them. I don't know, because the intermediate value theorem only works if the outputs are opposite signs. Because it's the same sign, it doesn't tell me anything. So for us, if this was on the test, this is where you'd stop because we don't have any other knowledge on how to factor this unless it would have factored by grouping, and it doesn't. So you couldn't actually do this one because we don't learn how to factor this until we get into a higher math. If we can't find some of the rational zeros right out of the gate to get us down to a quadratic, then we stop at this point. Okay? Any other questions? Everyone's tired, and we all had a 3-day weekend. How did that happen? Any other questions on homework or anything else? So we have two theorems that we can use. One is the factor theorem. The factor theorem states that if f of c produces 0, then f minus c is a factor. The remainder theorem says if f of c is equal to some number, we'll call it number, then that number is the remainder. When you divide f of x by x minus c. So which one of those two theorems I just gave you is going to be important to answer this question?
The second one.
Okay. So what is f of 3?
Would it be -5
Yep.
over x?
Nope. It's negative 5.
Just -5?
Yep.
That's it?
Yep.
Yeah, how do you?
Can you do that again?
You just gave me the So we have two theorems, the factor and the remainder theorem. The factor theorem says when I plug that c value in, then x minus c is a factor. The remainder theorem says the same thing, but you may or may not get 0, right? You just get some number. So if you divide a polynomial by x minus c, your remainder would have been the exact same answer as if you would have put in
Oh,
c into that function.
I'm gonna pretend like I understand that.
Okay, well, let's just do one, okay? So I'm going to give you a polynomial, right? So we have x squared plus 3x plus 2. And I want you to do synthetic division for x minus 1. Do synthetic division for x minus 1. So I'll give you a moment to set up the synthetic division and do it for x minus 1. For synthetic division.
Drop the 1.
Drop the 1.
1 times 1 is 1, so it's 2.
So 1 times 1 is 1, and then 3 plus 1 is,
Oh, 4.
and then what?
And then you multiply 1 by 4, so you get 4 because x1. The remainder is 6.
Now, take that function and put in 1 and tell me what you get. So the factor slash remainder theorem says, if that would have been 0, then x minus 1 would have been a factor. Because it's not 0, whatever kicks out is my remainder. Notice how this number was my remainder, which is exactly as I would have put that in there. So going back to this question, it is -5 because when I do synthetic division, or long division, and my remainder was -5, then that must be what I had if I would have put in 3 in there. We use the factor remainder theorem to take our polynomials and start to drop it down by powers enough that we could get to a quadratic. So if it equals 0, that's a factor, and I'll do synthetic division. If it's not 0, that's my remainder, and I keep moving. Does that answer your question? Okay. What else? Anything else? Okay, then let me go out. So step by step, the first thing I'm going to do is, all right, so going through this step by step, the first thing I'm going to do is use a rational zeros theorem to determine what my possible zeros are going to be. So I find my constant. My constant is -10. So I'm going to list out all the possible ways I can get to -10. So positive and -1, 2, 5, and 10. Those are the possible ways to get there. Then I look at my leading coefficient, which happens to be +1, and the only way I can get there is positive and -1. By the rational zeros theorem, I take all of the factors of my constant, and I put them over the factors of my leading coefficient and every combination thereof. Well, because my leading coefficient is 1, this is going to be fairly straightforward, because they're all going to be over 1. So my possible zeros are positive and -1, 2, 5, and 10. Those are the possible zeros. They're not all the zeros, they're the possible rational zeros. That being said, I may get numbers that are not rational. So I may get like a square root of something, and that could happen. And I may get complex. That could happen as well. But these are the possible rational zeros. Now I'm going to use Descartes. Descartes' rule of sign says, I go to my original function, and I look for the sign change between each term. So it changed once here, it changed a second time here, and it changed a third time here. So there are 3 times the sign changes between terms. So that tells me by Descartes' rule of sign that I have 3 or 1 positive real root, or 0. Remember, Descartes, you always drop down by a power of 2. To find my negative roots is I have to put in a negative x into my original function. So I put a negative x into my original function, and I have x to the fourth. That one isn't going to change when I put in a negative number because it's to a power 4. Minus 5x to the third, minus 27x squared, minus 31x minus 10. So the only ones that change sign when you put in a negative x are the ones that have odd powers. So then I look to see, okay, did this one change sign? Is that the only place it changed sign? Yeah, so I have one negative real root, or 0. So I'm guaranteed one positive and one negative. Now I start with the easiest. So after I've done Descartes, so the first thing I do is this. So this is my first step. Here's step 1. Step 2 is I use Descartes. The reason I do that is just so I know that I'm guaranteed or not guaranteed any zeros. So the next thing I'm going to do, step 3, is I'm either going to use synthetic division a lot, or I'm going to use the factor remainder theorem. I'm kind of partial to the factor remainder theorem, so I'm going to put in f of 1. That's my first choice. So I usually choose the easiest ones, which is 1 and negative 1. So I put in 1 and negative 1. So I'm going to put in 1, and I get 1 to the fourth plus 5 times 1 to the third minus 27 times 1 squared plus 31 times 1 minus 10. So I get my trusty calculator out, and I determine whether or not that equals 0 or not. So I'll wait till you tell me whether or not it equals 0. Okay, so that equals 0. What that tells me is I found one of my zeros. I found a positive 1, so I know positive 1 is going to work. Now, I can go into synthetic division right now and drop this down to a power of 3. That works. Or I can wait till I find a second one. It doesn't matter. What do you all want to do? Do you want to find a second one, or do you want to just start dropping this down by a power? Sure. So let's do 1, and then I do synthetic. So 1, 5, negative 27, 31, and negative 10. So x to the fourth, x to the third, x squared, x, and then my constant. And I always label the top so I know that when I drop it down by a power, I know what I'm at, and also that I make sure I've got all my coefficients in there. Okay, so I drop 1, and then 1 times 1 is 1. That gives me 6, then 6, and then this gives me, what, negative 21, and this gives me 10, and then 10, and then 0. So where I'm at now is my new polynomial, where I'm at here, the part of the polynomial that is still left remaining, is x cubed plus 6x squared minus 21x plus 10. Now, my same kind of rational zeros theorem I could use again, but that's still 10, so it's not going to help me to do a second one. If that number would have been, say, 5, then I know up here, so if that, say my constant would have been 10, or it would have been 5 instead, is I could have gone back up here and marked out everything that is not a multiple of 5. Yep. But because it's 10, I didn't gain anything by that extra step of trying to lose my zeros. So I'm going to do the same thing, but now I'm going to use this one, right? So I still have the same choices: 1, negative 1, 2, negative 2, 5, negative 5, 10, and negative 10. So I already found one positive. Here's my one positive right here. So I'm going to see if there's a second positive. So I'm going to try 1 again, because I like 1. 1's pretty cool to start with. So I'm going to try 1 again. So f of 1 is 1 plus 6 minus 21 plus 10. Does that give me 0? Nope. So I know that 1 isn't going to work, so let's try 2. So f of 2. So I have 2 cubed plus 6 times 2 squared minus 21 times 2 plus 10. Does that give me 0? So this gives me 0. That means that I have my second 0. So since I found my second 0, I'm going to come back up to, let me go back up to my,
Why didn't you, since we already figured out 1 was a factor, why did we put it in again?
because we may have repeating. So it doesn't have to be unique factors. It just needs to be a positive number. So 1's an easy one to check. So now I go back to my synthetic division, and this time I'm going to use that bottom line as my top row, and I'm going to use 2. So I do 2, so 1 comes down, 2 goes up. This gives me 8, and then 16 minus 5, negative 10. So I end up with x squared plus 8x minus 5. Now this doesn't factor, so I'm stuck with a quadratic. Now I've got it down to a power of 2. I can use a quadratic where a equals 1, b equals 8, and c equals negative 5. So I'm going to throw this in the quadratic, and so I've got x is equal to negative 8 plus or minus the square root of 8 squared minus 4 multiplied by 1 multiplied by negative 5 all over 2. So I end up with x is equal to negative 8 plus or minus 64 plus 20 all over 2. X is equal to negative 8 plus or minus 84 divided by 2. In 84, do I have any perfect squares I can factor out of there? Any perfect squared numbers? The square root of 84, how can I write that as a perfect square times something else? 4 goes in there, right?
Yeah.
So I can write that as the square root of 4 times 21, which equals 2 square root of 21. Do you agree to that? Okay. So then this is 8 plus or minus 2 root 21 all over 2. And the reason I took that step is because I want this to not be a fraction. And so I end up with 4 plus or minus 21, or square root of 21. Now, what I have is x is equal to 4 plus the square root of 21, and x is equal to negative, or positive 4 minus the square root of 21. So my zeros are this. It is those two that I just found. It was the one that I found before, and it was my 2 that I also found. So those are my zeros. 2 of them are not nice. So those are my zeros. My factors then, when I take this and I factor my polynomial, my original polynomial is going to factor into x minus 1, x minus 2, x minus 4 plus the square root of 21, and x minus 4 minus the square root of 21. And that's my linear factorization. 2 of those are not nice, but that is my linear factorization. So because this is the quadratic started out with a power of 4, I probably would have done this step right here. Specifically, I would have done the factor remainder theorem until I found 2 of them. And then I would have just done synthetic division one after the other like I did here. So after I found 2 of them, I would have just done the synthetic division twice, rather than doing that other step that I had in there and then going back to the synthetic. So I would have started out doing my f of 1, and then I would have done f of 2, see if it worked, and then f of 5 to see if it worked, if 2 didn't, right? I would have started out that way. And then once I found 2 of them, then I would have done the synthetic twice.
And so would you not be able to, since you only got like 2 zeros when you broke it down to a quadratic, if you already had 2 but you only got 2 from breaking it down, would you not be able to find all your zeros from just breaking it down to a quadratic?
So you will always find all your zeros when you break it down to a quadratic, if you can get it down to a quadratic. But those two zeros that I had, the ones that were not nice numbers, these here, I would not have got them with synthetic division. Those would not have shown up with synthetic division. Because when we do synthetic division, we are using the possible rational zeros. Square root of 21 is not a rational number. So because it's not a rational number, I would never find it with the way I did it with finding here's your possible rational zeros. Because these are the possible ones, but I'm not guaranteed these to be it, right? So these were the ones I thought could be possibly the zeros. You notice there's no square roots in there. So if your answer includes a square root, it's not going to be found by any of the steps up until we do the quadratic.
So if our first coefficient wasn't 1, just be doing measurement fractions.
Yeah, let me go out and take a look at one of those. Let me grab one of those so we can just start it. So if you're asked to find all the possible zeros, the first thing you're going to do is say, okay, my constant is 39. And the ways in which I can get to 39 is positive and negative 1. 3 will divide it, and it'll divide it 13 times, and then 20, and then 39. Those are my constant, the ways I can get 39. For my leading coefficient, it is 3, and the only way I can get there is 1 and 3, plus and minus. Okay? So my possible zeros is going to be every combination of my constant factors over my leading coefficient factors. So positive and negative 1, 3, 13, and 39. That's one way of getting them. Now that's putting 1 over 1, 3 over 1, 13 over 1, 39 over 1. Now I have to do the next grouping, which is 1 over 3, 3 over 3, which is 1, so I don't have to write that. I'll just write it this time, but then I'll just cross it through. 13 over 3, and then 39 over 3. 3 over 3 is just 1, so I didn't really need to write that. And 39 over 3 is just 13, so I didn't really need to write that. So these are all my possible zeros. And then we want to list them in increasing order. So my smallest number would have been negative 39 here, and then negative 13, and then negative 13 over 3. And then the next number should be negative 3. Then negative 1, negative 1/3, and then now it's going to be the positive ones. So 1/3, 1, 3, 13 over 3, 13, and 39. So that's how it's going to go from smallest to largest. Now what I'm going to do is I'm actually going to put these numbers in, right? Now I have a power of 4, so I'm going to get 4 zeros. So I'm going to start out with my easiest one. I'm going to use Descartes' rule of sign to tell me how many I'm going to expect in each direction. So Descartes' rule of sign says the only place it changes is here and here. So I have 2 or 0 positive real roots, or zeros, by Descartes. So I'm going to put in a negative x in there, so f of negative x. I get 3x to the 4th minus x to the 3rd minus 2x squared minus 5x plus 39. So I have one change here, and I have one change here. So I have 2 or 0 negative real roots, or zeros. So I'm not guaranteed any. I'm going to start with the easiest one. I'm going to start with 1. So this is that step. So now I'm at step 3. So I'm going to start with 1, f of 1. So I put 1 in there, and I get 3 plus 1 minus 2 plus 5 plus 39. Does that equal 0? No. So this does not equal 0. So over here, I would write no. So now my next one that's the easiest is 3. So I'm going to put 3 in there. 3 times 3 to the 4th plus 3 cubed minus 2 times 3 squared plus 5 times 3 plus 39. Is that likely to be 0?
No.
No. So I'm going to write no for that one. And again, I'm trying to avoid the fractions if I can. So now I'm going to try f of negative 1. So I put negative 1 in there, and I get 3 times negative 1 to the 4th, plus negative 1 to the 3rd, minus 2 times negative 1 squared, plus 5 times negative 1 plus 39. Does that equal 0?
No.
Yeah, I don't get it to be 0 either. So this does not equal 0. So this is a no. And now I'm going to try f of negative 3, because remember, I'm trying to avoid those fractions. So f of negative 3, so I have 3 times negative 3 to the 4th, plus negative 3 to the cubed, minus 2 times negative 3 squared, plus 5 times negative 3, plus 39. Does that equal 0? So 3 to the 4th is 81 times 3.
I gave my calculator an error.
So in your calculator, do 3 times 81 minus 27 minus 18 minus 15 plus 39.
3 times 81 minus 27 minus 18 minus 15 plus 39 equals 222.
So this does not equal 0, so I'd come up here and write no. So I was really kind of hoping to avoid the fractions, but it doesn't look like I'm going to be able to. So I'm going to do f of 1/3 and do the same thing, and I'm going to keep doing this until I get a yes or a no. All right? This one's going to be tedious, but it's going to get you to say, I can just plug these into my calculator and try to find them. Now, the other part that's happening here is if you're actually finding these numbers, right? So if I'm actually finding these numbers, then one of the things I can do is if I put in 1 and negative 1, if their signs are different, then I know one of those fractions have to work by the intermediate value theorem. If I put in 1 and negative 1 and they're the same sign, the intermediate value theorem does not help. So when I put in 1, what did I get? Did I get a positive number or a negative number? It was positive, right? So not only is it not 0, but it's a positive number. When I put in negative 1, did I get a negative number out?
You got a positive as well.
It's also positive, so that actually the intermediate value theorem is not going to help me. So I may have crossed at negative 1/3 and at 1/3 because the intermediate value theorem didn't help me.
So what does that mean again?
So the intermediate value theorem states, if my signs change on the output, I had to have crossed between them, because polynomials are smooth, continuous curves, which means if I were to draw a polynomial, any polynomial, right? If I draw any polynomial, if that's my polynomial, then I have to be able to draw it from left to right without picking up my pen.
That's right.
So if my output, as an example, I chose this number, my output was positive and my output was negative on this one, when I chose that number, say this is A and I chose B. Since f of A is positive and f of B is negative, I had to have crossed between them. But if I put in, say, C and it's also negative, if f of B is negative and f of C is negative, I don't know if I crossed or not. So the intermediate value theorem only works if the sign changes. Okay? All right, and I will upload this tonight, and I'll put it underneath, right underneath where it says notes and videos. So this one's a long one. It has a lot going on. What happened there? Wait a minute. Oh.